All right, let's just dive right in. Deep inside your computer, your phone, whatever device you're using, there is a silent genius at work. It's making trillions of decisions every single second. So today, we're going to pull back the curtain on this hidden mastermind and uncover the secrets of the operating system.
I mean, seriously, think about what your computer is doing right now. You've probably got music streaming, a web browser with who knows how many tabs open, notifications popping up. How in the world does one machine do all of that at once and make it look so easy? You know, it really does feel like magic, but it's not. It's just some absolutely brilliant engineering.
And that's the secret sauce, right there, the operating system, or the OS. Think of it like the conductor of an orchestra or the air traffic controller for all your data. It is the mastermind that coordinates every single thing. Let's be real, without it, your computer is just an expensive, useless box of parts. So, we're going to explore the 3 biggest puzzles the OS has to solve to make all of this possible.
Okay, first up, the incredible juggling act. Every single app you run, whether it's a massive video game or just a simple calculator, is demanding the computer's attention. So how does the OS handle all these competing requests without dropping all the balls?
Well, the first step is actually a really clever bit of thinking. The OS doesn't see Chrome or Spotify. Nope, it sees something called a process. And a process is just a program that's currently running. That's it. It's a simple idea, but it's incredibly powerful because it lets the OS manage everything with one consistent set of rules.
And, a process isn't just on or off. It has a whole life cycle. As you can see here, it starts out as new, then it moves to ready, kind of like waiting in line for its turn. Then it gets its moment in the spotlight in the running state, and it might get put on hold or blocked if it's waiting for, say, a file to download. And then eventually, it's terminated. The OS is the manager for this entire journey, for every single process.
Okay, but here is the real head-scratcher. Your computer's main brain, the CPU, can fundamentally only do one single thing at any given instant. One. So how on earth does it create this flawless illusion that it's doing a million things at the same time?
The secret is a technique called process scheduling. See, the OS has this little component called a scheduler, and it works at lightning speed, constantly switching the CPU's focus between different processes. We're talking thousands, even millions of times a second. It happens so fast that to us, it just looks like everything is running all at once. It's all about squeezing every last drop of performance out of your hardware.
So how does the scheduler decide who's next? Well, there are a bunch of different strategies, and each one has its pros and cons. Take first come, first served. Sounds fair, right? It's just like a line at the bank. But what if the person in front of you has a really complicated transaction? You get a traffic jam, which we call the convoy effect. That's when your computer feels like it's stuck. A totally different way is round robin. This gives every single process a tiny slice of time, then moves to the next and the next. This is the magic that makes your machine feel so responsive and snappy. The big takeaway here is that there's no single best answer. It's all about trade-offs.
Okay, so the OS is juggling all these tasks. Awesome. But where do all those running programs actually live? That brings us to our second huge challenge, managing the computer's limited physical memory, its RAM.
Now, the simplest way you might think to do this is to just put each program into one big, solid block of memory. That's the contiguous approach. But the problem is, you end up with all these weird little unusable gaps between the programs. It's super wasteful. So the much smarter solution is to allow a single program to be scattered all over the place in memory.
And this is how they pull it off. It's a brilliant technique called paging. The OS takes a program and chops it up into these little fixed-sized pieces called pages. Then it divides up the physical RAM into same-sized slots called frames. And the real magic is the page table. You can think of it like an address book that keeps track of where every single page is. This lets the OS play Tetris with your memory, tucking pieces in wherever they fit. It's an amazing solution to the puzzle.
And that concept leads to an even bigger idea: virtual memory. Seriously, this might be the OS's greatest magic trick of all. It lets your computer pretend it has way more RAM than it actually does by using your hard drive as a sort of emergency overflow area. This is exactly how you're able to run those massive programs that are technically way bigger than your computer's physical RAM. It's incredible.
But there's always a catch, isn't there? This magic has its limits. Take a look at this graph. As you add more and more programs, your computer gets more productive, but only up to a point. If you push it too far, the system starts spending all of its time just shuffling data back and forth between the RAM and the hard drive, and no time at all doing any real work. That collapse, that's called thrashing. And that is the exact feeling you get when your computer grinds to a halt because you have 100 browser tabs open.
So let's recap.
We're juggling tasks, we're managing memory, but what happens when two or more programs need the exact same resource, like the printer, at the exact same time? This leads us to our third and final problem: how to avoid a total system gridlock. To get our heads around this, let's use a classic analogy: the dining philosopher's problem. Picture 5 philosophers at a round table. To eat, each one needs 2 chopsticks. Now, what happens if every single one of them, in perfect sync, picks up the chopstick to their left? Well, now nobody can pick up the chopstick on their right. Nobody can eat. They're all just stuck, waiting forever. They starve.
That little story is a perfect metaphor for what we call a deadlock in a computer. It's a digital traffic jam where 2 or more programs are completely frozen because each one is waiting for a resource that the other one is holding hostage. Nothing can move forward. The system is just stuck.
Now, for a deadlock to actually happen, all 4 of these conditions you see here have to be met at the exact same time. You need a resource that can't be shared. You need a program holding one thing while waiting for another. You need a rule that says you can't just snatch a resource away. And finally, you need that circular chain of waiting, just like our philosophers. The OS's job is to be the smart one in the room and use clever algorithms to make sure these 4 things never all line up at once.
So let's zoom back out and look at the big picture. What have we learned here? We've seen that the operating system isn't just one thing. It's a whole collection of brilliant solutions to some incredibly difficult problems. It solves the juggling problem with lightning-fast scheduling. It solves the finite memory puzzle with that elegant system of paging and virtual memory. And it acts as the ultimate traffic cop to prevent the digital gridlock of deadlock. You know, these aren't minor details. These are the core functions that make modern computing even possible.
So, if there's one thing to take away from all this, it's that the OS is the true unsung hero. It's the invisible, foundational layer of software that turns a lifeless piece of silicon and metal into the powerful, responsive tool that you rely on every single day.
And that just leaves us with a final, thought-provoking question. The world of computing is always changing, right? Now we have AI, billions of tiny smart devices, massive cloud data centers. The puzzles are just getting more and more complex. So what new scheduling algorithms, what new memory tricks, what new ingenious solutions will the next generation of operating systems